This I am going to give as an exercise. I will give some homework. Exercise is, I computed g of x, right, for point source at 0. I showed that to be this function. Now do the Fourier transform of this, then you should get this. G of k should be minus 1 over k squared. This is straightforward. But other way around, given this, derive this for 1D. Derive this for 1D. That is not so straightforward, but I recommend that you do it. So I did g of x in 1D. Now given that you can compute g of k, you should verify that is 1 minus 1 by k squared, and vice versa. For minus 1 over k squared in 1D, you get this function. Okay. So this I will give as a homework, and you do it yourself. Now let us compute this in 3D. It is an interesting exercise to do it in 3D. I will do some of this integral, because you need to know how to do this integral. Okay. Now in 3D, well, I forgot the minus sign. You should put a minus sign, minus 1 over k squared, no. G of k is 1 over k squared minus sign, and my response is g of r. I am assuming source is at 0. When I should say that if your source is not 0, then this part is not r, but r minus r prime. Okay. But I do not want to carry this r prime all the time. So I assume source to be at 0, and if you really need it, then you need to put that, otherwise it is okay to ignore it. Okay. So let us do this integral. I mean, it is not difficult, but it is nice to see how to do this. So my integral is over k, but my r is fixed, no. In the integral, r is a fixed vector, yes or no. So choose r along z axis. This is my vector r. That is number 1. Is my choice. My integral, okay, I am choosing my r vector along z axis. Okay. I mean, if my source is sitting here, and if I am measuring my potential in some direction, I choose that to be my z axis. Okay. Now k is of course varying, right. So my k vector can be anywhere, and this angle is theta. So we will use spherical geometry, spherical coordinate system. R, well, the magnitude is k, and d theta d phi. Okay. So k is varying on a sphere. In fact, not on a sphere, k goes from 0 to infinity, the magnitude of k. So 1 by 2 pi cube, minus sign I keep it outside, and integral. Now dk is k square dk d cos theta d phi. Now this is azimuthal symmetry. If I let go in that direction, my integral is unchanged, it is not function of phi. So I do the d phi integral in one shot, and 2 pi will come out. D phi is 2 pi, no, this azimuthal angle 2 pi. So d phi I do not need to worry, and k square is here, and I get e to power I k dot r. What is that? K dot r cos theta, no. So e to power I k r cos theta, that is it. Now my k goes from 0 to infinity, and cos theta goes from minus 1 to plus 1, or theta goes from 0 to pi. So this cancels, 1 over 2 pi squared minus sign, k squared cancels. Now what is this integral? D cos theta e to power I k r cos theta. So this we can call a variable s. So this will be e to power I k s goes from minus 1 to 1. So e to power I k minus I k by k r I k r. So, that is the d cos theta integral, which has been done in your quantum course, I am sure. Okay. So, the cos theta integral also is done, dk, and k goes from 0 to infinity. Okay. Now, what is this? I k r e to the power minus I k r is 2 I sin k r. Yes. So, minus 2 pi squared, this minus I need to worry about it bit later, sin k r 2 I divided by I k r. Okay. So, I cancels, and that is what we get, k r and great, fine. Now, what should I do after this? So, these functions, these are here and this is a dk. So, one thing is to make this integral non-dimensional. This integral has, what is the dimension of this integral? 1 by length, right. So, I want to make it non-dimensional. So, multiply this by r is a number, for this integral k is variable, but r is a number. So, multiply by r and divide by r, fine. Now, this integral, in fact, we already know what that is, pi by 2. No, this we already did, sin x by x dx, this is pi by 2. So, this is 2 pi squared 1 by r and pi by 2. Okay. So, 1 pi cancels, and so I get 4 pi r. Now, there is a minus sign which is 8 pi r. So, there is a 2 somewhere, 2 is this 2 is there, the 2 cancels, the 2 cancels with that. So, it is 1 by 4 pi r. Okay. This is the, in fact, we know this potential, right. For a point charge in 3D, the potential is 1 over r, other than this prefactor. In fact, prefactor is also correct. Okay. Only thing I need to worry about is the sign. This is a negative, but I should get positive. Well, let us put a negative here. I think is because Laplacian I put a negative. So, for 1 over k squared, the integral is 1 over r. If you put a minus, then I will get minus 4 pi r. Okay. So, this is how we derive it. In fact, we know it, this is correct. I am not 100% sure about the sign, but you will verify that part. Okay. So, this is how you do the integral, 3D integral. Most of the time you will be basically doing this, choose your r along z axis and do this integral. Sometimes of course, we do not use sin k r, I am going to just show you some more integrals, but it is straightforward, no, but you should know how to do this. Okay. So, any questions on what I did so far? These are straightforward definitions, but you need to remember this these answers. The Green's functions in for Laplacian operator is 1 over k squared, and in real space it is, if you know the potential electrostatics, you can easily do this. What about in 2D? What is the answer in 2D? 2D is log r. Okay. 2D potential is log r, for line charge potential is log r, and you should be able to derive it. Okay. The derivation is not that straightforward, it involves Bessel function, but you should be able to, well, I mean that is a exercise for interested students. GFR is log of r. GFR is potential for a point source, and if you know electrostatic answer, you should just be here. Okay. So, any questions on this? Well, basically in general, yes. So, Fourier, it is 1 over k squared irrespective of the boundary condition. Okay. That state came from the formula GFR. Now, It is a very good question. Finally, you need to compute this potential in the real space. So, given 1 over k squared, I need to compute g of r in real space, and that is where I need to put the boundary condition. Okay. So, inversion from Fourier to real will involve boundary condition, but in field theory we will assume infinity. So, that is where we are avoiding this boundary condition details. Okay. So, like in quantum electrodynamics, you are not considering walls, these photons are just going to infinity, and so we are too far away from the walls. Okay. So, that works reasonably well for most of the time, but of course, fluid in a cavity we need the boundary condition. So, in fact, there is another advantage of Green's function in Fourier space, you do not need the boundary condition, most of the time you do not need the boundary condition, but when you get the real space then you need the boundary condition, but here we will assume infinite extent. Okay. So, this is the one place where we can stop.